Good morning, everybody. Well, thank you very much for coming along to this workshop. It looks very interesting. And, well, let's get started. We have two talks this morning that are linked to one another by Jacob and Yufei. And Jacob's going to give the first one, as you can see, it's on tower-type bands for Roths theorem, popular differences.
Thank you, Ben. It's a pleasure to start off the Combinatorics workshop. So I'll be talking about joint work with Hui Tuan Pham. He's an undergraduate at Stanford University, and Yufei Zhao, who recently joined the faculty at MIT. So we'll start with Roth's theorem, which is a classical result in additive combinatorics. It says that if you have a subset of the first n positive integers, and it contains no three-term arithmetic progression, then the subset is sparse. So it has only little o of n elements. Roth's proof actually gives a bound of big O of n divided by log n. The way his proof works is instead of looking in 1 to n, it's equivalent to look in the cyclic group with big N elements, and up to a constant factor. And if there's no large non-trivial Fourier coefficient, then there's a nice formula for the number of three-term arithmetic regressions in terms of these Fourier coefficients. And if they're all small, then you basically get the random bound. So if your subset is density alpha, you'd have density of three-term arithmetic regressions about alpha cubed, as if your set was random. So there is going to be a large Fourier coefficient. You can use that to find a fairly large arithmetic regression, roughly square root of n size, in which the density goes up. So you had density alpha to start with, and you can find this arithmetic regression of length roughly square root of n, where you get density about alpha plus alpha squared. And then you just iterate, because now you have this on an arithmetic regression that's equivalent to doing this on an interval. And you just now have this denser subset and a relatively denser subset. You can just iterate that, and when you do that, you eventually get this bound. There's been improvements over the years by Heath Brown, Samaretti, Bourgain, Sanders, and Bloom. There are two types of improvements. One of the big improvements, the idea due to Bourgain, is to use these things called Bohr sets. So instead of going from, it's pretty wasteful to go down to an arithmetic regression of length roughly square root of n. And so you'd like a large set that behaves very much like an arithmetic regression. These things are called Bohr sets, and where you get a density increment. You can indeed find such a set. But now you have to do Fourier analysis on Bohr sets, which is much more complicated. And it can be done, and that allows you to get a power of log n. Another thing you can do is instead of looking at the largest Fourier coefficient, you can look at the large ones and try to show that they have some additive structure and be able to improve the bound by using the ones of using the Fourier coefficients that are large to get a bigger increment. Look at their additive structure. And the best known bound right now, due to Bloom, which improves a bit on the bound of Sanders, the proofs are different, or substantially different. And it gives roughly n over log n, and there's a power of log n. Still there. Now the best known lower bound is pretty far away. It's of the form n divided by e to the square root of log n. And there's a lot of evidence that suggests maybe the lower bound is closer to the truth. In particular, three-term arithmetic regression is three numbers x, y, and z that...
How about the recent green tau bound? They have a four-term progression.
For four-term, it's a power of log. Yeah, so I'm just talking about three-term here.
But that also implies three-term, right?
Right, but that's not beating this. This is still that's still a power of log n. It's just not. It's not one there. Yeah.
Okay.
And right, so it's recently available, but that's been known for a while now. Instead of just getting one three-term arithmetic regression, Varnavides a long time ago noticed that you can bootstrap this to get a lot of three-term arithmetic regressions. If you have a subset of the first n integers of density alpha, then you not just get you don't only get one arithmetic progression, but you get at least a constant times the total number of potential three-term progressions. So you get some constant depending on alpha times n squared three-term arithmetic progressions. And the exact dependence between this alpha and c of alpha is very closely tied to the bounds in Roth's theorem. So you can show in both directions that it's very closely tied together. Okay, so you can look at, instead of looking in the cyclic group, you can look at the same sort of question in other abelian groups. You'd like a large subset of an abelian group without a three-term arithmetic progression, and the one that people have studied a lot is f3 to the n. So how large can a subset of f3 to the n be without a three-term arithmetic progression? This is known as the Capset problem. It's also a famous problem because it's related to a bunch of other well-known problems in combinatorics and computer science. So it's a variant of Roth's theorem, but it also is closely tied to the sunflower conjecture in combinatorics and the exponent for matrix multiplications related, which is a well-known problem in computer science. And you can try to see how large such a subset can be. There was an old result from the early 80s of Brown and Buhler that shows that such a subset has to have size little o(n). And then there's a very nice observation of Meshulam, which gives a bound of big O of n divided by log n. Big N here is 3 to the little n, is the number of elements of f3 to the n. Meshulam's proof is really Roth's proof adapted to the f3 to the n setting. So when you get a large Fourier coefficient, you still have the same formula for the number of three-term arithmetic regressions in terms of these Fourier coefficients. And so there should be a large Fourier coefficient. And if there is a large Fourier coefficient, it is essentially equivalent to saying that there's going to be a codimension 1 subspace, affine subspace, where the density goes up. So you have this affine subspace of dimension n minus 1, and instead of having density alpha, you now have density alpha plus something like alpha squared. And so instead of going from big N to square root of n, you go from big N to n over 3. And you iterate this, and you get the bound big O n over log n. It's a very clean, nice argument. It's simpler than Roth's proof. And using the additive structure of the large Fourier coefficients, this is a difficult result of Bateman and Katz, where they improve the exponent of log n to 1 plus some tiny constant c. And they're really using a lot of the tools from Additive Combinatorics. It's a long paper. A little over a year ago, there was a breakthrough by Krut, Lev, and Peter Pot on this problem. And so as you saw, the previous results all were based on Fourier analysis and adapting those techniques. And this was a very nice result, and it used a very different technique. They were looking at z4 to the n, and the proof used this polynomial method, and it's beautiful and short. And they got, instead of a bound that looks like big N divided by something small, they got big N to the 1 minus a little exponent for z4 to the n instead of this f3 to the n. And within a few days, Ellenberg and Geisweit independently discovered that their proof can be adapted to f3 to the n and more generally fp to the n. So if you have a subset of fp to the n with no three-term arithmetic regression, then it's small. You get some exponential constant here that's less than p to the n. P to the 1 minus some cp, and the cp is an explicit constant. You can write down what it is. The cp is roughly, it's on the order of 1 over log p, if you're wondering what it looks like. And soon afterwards, it was observed by many people. There was a group of 7 authors in a paper where they were looking at more general settings, and also Noga alone, where they showed that not only does it work for three-term arithmetic regressions, but it works for something called the multicolor sum-free problem. So if you have 3 subsets of fp to the n, x's and y's, xi's, yi's, and zi's, 3 subsets, and they each have size n. And the only solutions to xi plus yj plus zk equals 0 are those in which I equals j equals k. Then m is at the number of elements in each of these 3 subsets is at most the same bound that we had before. Now, why is this a generalization of this result? Well, if you let x and z be the set A and y be minus 2 times the elements in A, then you get exactly this condition satisfied. So you have these trivial 3-term progressions, which are an element 3 times, so common difference 0. While we don't know what the right exponential constant is for the Capset problem, for the multicolor sum-free problem, Fu and Kleinberg already had a construction which matched this in F2, over F2. So when P is 2, Fu and Kleinberg showed that this exponent was sharp much earlier. So they had a construction which gave a lower bound. And then later, Kleinberg, Saw, and Inspire proved that it was tight for larger P. It was conditional on a conjecture that they had, which was later proved independently by Sergei Norin and Luke Peabody. So there's been a lot of work on this over the last year, and many other related problems.
So they're getting P and P to the 1 minus CP, they're getting exactly the same constant out there?
So the exact same exponential constant, there's a minus little o1 in the exponent. So 1 minus CP minus little o1, there's a lower order term. But the exponential constant's tight for the multicolor sum-free. Okay. So I'm going to turn to graph theory, and we'll pull back to the additive combinatorics shortly. There was a famous result of Samaretti called the regularity lemma, which has been very useful for these sorts of questions. Samaretti originally developed it, or at least an early version of it, in his proof of Samaretti's theorem that then subsets of the integers contain arbitrarily long arithmetic progressions, so this generalization of Roth's theorem. So it says, so we still need some definitions. If you have 2 vertex subsets x and y of a graph G, dxy denotes a density of pairs in x times y that are edges. And you call a pair xy epsilon regular, so these are a pair of subsets of your graph, vertex subsets, if whenever you take a subset A of x, which is at least an epsilon fraction of x, and a subset B of y, which is at least an epsilon subset of y, the density between A and B is roughly the same as the density between x and y, the two sets that they came from. They're within epsilon of each other, which tells you that the graph looks very uniform between these 2 sets, x and y. And the regularity lemma says that for every epsilon greater than 0, there's a k of epsilon, so that every graph has an equitable vertex partition. So that's a partition of the vertices into equal parts. Maybe they differ in size by at most 1 due to modularity constraints, so that all but an epsilon fraction of the pairs of parts are epsilon regular. Samaretti's proof is a nice density increment argument. It gives an upper bound on k of epsilon, which is a tower of 2s of height, a power of 1 over epsilon. And Gowers showed that, gave a lower bound probabilistic construction that shows that this is actually necessary. So that this k of epsilon in Samaretti's regularity lemma has to be a tower of 2s of height, a power of 1 over epsilon. So this is a bit unfortunate for applications in combinatorics and additive combinatorics and these and other areas, because there's a lot of things that you can use this for. There's many, many applications, and the bounds you get are horrible. There are these enormous tower type bounds, and we expect in its applications generally that there should be much better bounds. And so this was a major program in combinatorics to get rid of the regularity lemma. So you want to find alternative proofs of the applications which avoid using the regularity lemma and give improved bounds. So you really want to understand the applications themselves. And the person who's really been pushing this to get rid of using the regularity lemma has been Samaretti. He's the one who's been pushing this program the most in recent years. So one application of the that's been a fruitful direction, it itself has many applications. The regularity lemma is a triangle removal lemma. So for every epsilon greater than 0, there's a delta greater than 0 such that if an n-vertex graph has few triangles, so at most delta n cubed triangles, so a graph on n vertices can have up to n choose 3 triangles. This is saying if you have few triangles, then you can delete a small number of edges and remove all the triangles. So you remove at most epsilon n squared edges and remove all the triangles. And it has many applications in extremal graph theory, additive combinatorics, theoretical computer science, and combinatorics. For example, there's a very nice proof of Roth's theorem that we saw earlier using the triangle removal lemma. It gives a very bad bound based on what we know currently for Roth's theorem, but maybe if you could get good bounds for the triangle removal lemma, you'd end up getting good bounds for Roth's theorem. So the proof uses Semray's regularity lemma. You take a decomposition and you delete the edges between pairs which are either sparse or not regular. And you haven't deleted many edges in this process. And if there was any triangle that remained, the 3 vertices would go between parts. The 3 vertices between them, the edges, would go between parts that are both dense and regular, and you get a lot of triangles using a counting lemma for triangles. And the question that's been asked many times is to find a new proof which gives a better bound. And the only improvement we have, instead of getting a tower of 2s of height, a power of 1 over epsilon, the tower height has been improved from a power of 1 over epsilon to logarithmic in 1 over epsilon. It's still a tower bound, and it's very large. And in the other direction, the best known lower bound we have is going through the Barron construction that we saw earlier and gives just a slightly super polynomial lower bound. So there's this enormous gap. It doesn't seem like either of them should be correct. And it's a very nice question to try to improve the bounds for this, I think. Now, about 15 years ago, Ben Green introduced an arithmetic regularity lemma in order to introduce new applications in number theory of this idea. So I'm going to state a special case of this arithmetic regularity lemma. Suppose you have a subset A of f3 to the n. So I'm just doing it in the setting of f3 to the n. In the general case, he proves it for abelian groups, and it uses Bohr sets, and to state it is more involved, and so we're going to look at a special case just to see what's going on here. The density of the set A in a subspace S, so we have a subspace S of f3 to the n, is just a fraction of the subspace that is in A. That's the density. And then we need a notion of regularity. So we look at a translate of the subspace S. This is just a coset of S. This is an affine subspace, which is just a translate. And we call it epsilon regular if whenever we have a codimension 1 affine subspace T of S plus X. So codimension 1, so this is just going to end up being some special types of subsets which are a third of the size of S plus X. And we look at the density of A inside that affine subspace. And if that differs from the density of A inside, so this codimension 1 affine subspace of S plus X, if the density of A in this affine subspace of this is within epsilon of the density of A within this affine subspace, then you call the subspace S epsilon regular. So that should hold for every codimension 1 affine subspace. This condition is typically stated in terms of Fourier coefficients. Up to a small change, it's the same as saying the Fourier coefficients, the non-trivial Fourier coefficients are all small. And then a subspace S is epsilon regular if all but an epsilon fraction of the translates of S are epsilon regular. So then the arithmetic regularity lemma says, so Green's arithmetic regularity lemma, in this instance of f3 to the n, for each epsilon greater than 0, there's an m of epsilon such that for any subset of f3 to the n, there's an epsilon regular subspace S of codimension at most m of epsilon. So bounded codimension. And just like before, the m of epsilon is a tower of 2s of height, a power of 1 over epsilon. And there's a matching lower bound construction that shows you that it's a power of 1 over epsilon.
This is not quite a regularity. Is it just one subspace? This is not.
This no. So this is So the definition for the subspace S, this is a subspace with 0, is that all but an epsilon fraction of the translates of S are epsilon regular. So it is the full regularity lemma, not just finding one affine subspace. Okay. So in his paper, Ben Green proved two nice generalizations of Roth's theorem. One of them is called the arithmetic triangle removal lemma. A triangle in Fp to the n is a triple x, y, z of points with x plus y plus z equals 0. And then the arithmetic triangle removal lemma says for every epsilon greater than 0 in prime p, there's a delta greater than 0, such that if x, y, and z are subsets of Fp to the n, and there's few triangles in x times y times z, notice that if you have an x and a y, there's a unique z that makes a triangle with it. It's minus x minus y, right? So there's going to be p to the 2 to the n, p to the 2n triangles in Fp to the n. So you're saying if between x times y times z there's few triangles, then we can delete epsilon pn points from x, y, and z and remove all triangles. That's the arithmetic triangle removal lemma. And it uses this arithmetic regularity lemma. It gives a bound on 1 over delta, which is this big tower. Kroll, Sarah, and Vina, several years later, so I stated this for Fp to the n. The Ben Green's proof, and what he shows there is that it actually works for any abelian group. He's using Fourier analysis there. And Kroll, Sarah, and Vina gave a new proof using the graph triangle removal lemma that extends to non-abelian groups, so for all groups. And because you get this, you can use the triangle removal lemma, you get a little bit better bound, which is logarithmic in 1 over epsilon tower height as an upper bound on 1 over delta. There was also another proof through Fourier that gave such an improvement. But Ben Green asked to improve the bound in the arithmetic triangle removal lemma. In particular, maybe delta is polynomial in 1 over epsilon. And there was a lot of work on this problem. So there were lower bound constructions that were all polynomial, and but it was unclear what the right bound should be. And then last year, with Laszlo Miklos Lovas, who just finished up his PhD with me, we proved that indeed the bound is polynomial, and we can even determine the exponent. And it's closely related to the multicolor sum free and Capset problem that we saw earlier. So the big CP, the exponent is 1 plus 1 over little CP, which is this explicit number. And so CP is on the order of log P, and this exponent CP is sharp. If you wanted to see the first few values, C2 is about 13.239. It's some strange thing. C3, you have to, so there's some optimization problem in order to figure out what these are. And you can write down what these exponents should be, but they get a bit complicated for the first few values. And then more recently, with Lisa Zauerman, we also proved a polynomial bound for the arithmetic k-cycle removal lemma. So instead of 3 sets, if you have k sets, and you look at a k-cycle as a sum of k elements, 1 from each of these sets, add up to 0, then there's an analog of the triangle removal lemma. For that, you get, instead of exponent 2, you would have k minus 1, and you can ask to get good bounds for that. And we proved that polynomial bound holds. We thought it would be kind of straightforward, that the techniques that we developed in this work, which uses some random sampling and combinatorial arguments, we thought maybe that should go through. And there's a serious problem with that technique. It doesn't go through. And we got stuck with that for a while, and it turned out to be a lot harder than we thought. And then eventually we discovered how to black box the lower values of the cycles in order to get the k-cycle case.
I mean, so it looks as if you can reduce one to the other, right?
Yes, but it's not easy.
Not so simple.
It's not as simple as it
Which
looks. Yeah, so it's not that short of a proof.
Even, okay.
Is there an easy direction?
So we thought it should be easier to do k-cycles than triangles and things of this, but and indeed we eventually reduce it to this, but it actually required a lot of work.
So you cannot just leave two of the sets as they are and replace.
No,
one set by the sum of-
that doesn't work. Yeah, yeah,
Okay, I don't see why, but okay.
yeah. And we don't know the right exponent for this, so we get a bound, but we don't know what the right bound is. Yeah. Okay. Okay, so that was the first application, and it would be interesting to get more general removal lemmas, whether or not we can get the polynomial bounds in those settings as well. Okay, so that was the first application. The second application that Ben Green had was a conjecture of Bergelsen, Host, and Roth, which is a strengthening of Roth's theorem. So if you have, for every epsilon greater than 0, there's going to be an n of epsilon, such that if you have a subset of 1 to n of density alpha, then if your set was taken at random, the density of 3-term arithmetic progressions would be roughly alpha cubed with high probability. But there are sets with much fewer total number of 3-term arithmetic progressions. And you can blow up the Barron construction to do that. So what Green's theorem says that while there are sets with much fewer total number of 3-term arithmetic progressions, there is going to be a non-zero D such that there are a lot of 3-term arithmetic progressions with common difference D, at least essentially the random bound up to epsilon. So alpha q minus epsilon times big N. And the proof used the arithmetic regularity lemma, and the natural question is, how large is this n of epsilon? So in recent work with Hui Pham and Yufei Zhao, we proved that n of epsilon grows as a tower of 2s of height logarithmic in 1 over epsilon. So both as a lower bound and an upper bound. And we'll try to explain the proof of that.
So is this fixing alpha as absolute constant?
So this is looking over all alpha. So if you fix alpha and epsilon, you can make an n alpha of epsilon. And this is going to be the supremum over all alpha of n alpha of epsilon, n alpha and epsilon.
What do you want this to hold for many d? So change the picture.
Sorry, what?
What do you want this to hold for like many d?
So you actually get many d in the proof. The number of d you get is going to be some constant depending on alpha times n. That constant depending on depending on epsilon, the constant depending on epsilon times n. That constant is 1 over a tower of 2s of height logarithmic in 1 over epsilon. So there's a constant fraction of them, but it depends on this epsilon, and that constant fraction is actually very small as a function of epsilon. Okay.
Should be because n epsilon is so large.
Right. Yeah. And the same result holds if you replace the interval 1 to n by any abelian group of odd order. And this is the first application of the regularity lemma where the tower type bound is shown to be needed. So there was this program I mentioned earlier to get rid of the regularity lemma. And this is the first time we see that one of these applications, the tower type bound you get really is necessary. So we knew for the regularity lemmas that this tower type bound was necessary, but we suspected with these applications there should be much better bounds. Okay, so I want to mention what happens in the case of fp to the n before going further. Again, fp to the n, there's this nice finite field model that's been very useful in Additive Combinatorics. There's a nice paper by Ben Green about this idea that you can prove things in the integers and other settings by first looking at fp to the n, trying to prove it there, and then using things like Bohr sets and other ideas in order to extend it to the general setting. So it's very helpful to have these subspaces. Let's look at the two-variable version. So we think of p as fixed here. Let np of alpha beta be the least integer such that if n is at least np of alpha beta, then every subset of fp to the n of density alpha, for every such subset, there's a non-zero d such that the density of three-term APs with common difference d is at least beta. So we looked at the one variable, not really changing the beta. Before the joint work of the three of us, there was work with Hoi Pham. We split up into two papers where we determined the tower height for np alpha beta up to an absolute constant factor plus an additive term that depends on p. And it turns out that there are several different ranges for np alpha beta where the tower height behaves differently in these different ranges. And we had to come up with different techniques for each of these different ranges. When beta is very small, less than alpha to the CP divided by 2, so alpha to the CP divided by 2, you can convince yourself that this is intimately related to the Capset problem. So actually the bounds here are going to be equivalent to the Capset to determining the bounds for the Capset problem, well, in fp to the n. And as you increase beta, it turns out that there's a density increment argument, and at each step, you want to use the results in the Capset problem, or rather the supersaturation version, which is something that follows from the arithmetic triangle removal lemma. And then there's matching construction, so at each step you do some version of the Capset problem. But so there's a bunch of different ranges, and I want to just mention one of the range when beta is half alpha cubed. So if you want half the random bound for what you get there is a tower whose height is on the order of log p times log 1 over alpha. So it's not log 1 over alpha, but log 1 over alpha. And again, this exact bound is because we know the Capset problem well now. And so at each step, you get some density increment, which is much larger than what you get when beta is very close to alpha cubed. And that allows you to bring the tower height down. Okay. So I want to present the proof of the upper bound of the log 1 over epsilon tower height. And there's a key lemma. If we have a subset of fp to the n, and H is a subspace of fp to the n, we're going to look at something that we call the mean cube density, which is the average of the density cubes of A in the affine translates of H. So we look at all the affine translates of H. We look at the density of A inside those translates. We cube those, and we look at the average value. Now, usually when you do regularity type density increment arguments, you often do the square instead of the cube. But there are other places where we use different functions here, and they've been useful in other problems. Here, cube is actually the right choice to make. It has to do with the fact that a three-term arithmetic progression comes from three variables. And if instead of your set A, you had a function from fp to the n to 0, 1, you can think of it as the characteristic function of A, but now you allow it to have values between 0 and 1. And if you made it constant on each of your affine translates of H, then the 3AP density with common difference inside H would be precisely this mean cube density. That allows for 0, but if your subspaces are big enough, the ones with density, the three-term progressions with common difference 0 are not substantial. Okay, so we're going to do a density increment argument involving this mean cube density. If you have a subspace H that's not too small, and for each non-zero D in fp to the n, the density of 3APs with common difference D in A is at most alpha q minus epsilon, then you can find a subspace of H, and you can bound the codimension of the subspace. It's at most essentially exponential in the codimension of H, such that the mean cube density of the difference between of H prime and alpha cubed essentially doubles. So from the previous value, so you get twice as large value of this b of H minus alpha cubed. And if you iterate this, so you start off, so we have this b of H for a subspace H. The value of the mean cube density, well, it's always going to be at least alpha cubed, and this is by convexity of the function f of x equals x cubed. And it's always at most alpha. So alpha is the set density, so it's the a over p to the n equals alpha. So it's always going to lie in here no matter what subspace H we pick. And if we start with H not equals fp to the n, and which has codimension 0, and we just iteratively apply this after I steps, we'll have a subspace hi, and b of hi will be, b of hi plus 1 will be greater than or equal to 2 of b of hi minus alpha cubed plus epsilon over 2, which is greater than or equal to, by induction, 2 to the I plus 1 minus 1 times epsilon over 2. There's a minus alpha cubed here that I'm missing. So now this b of hi plus 1, it can never get beyond alpha. So you're going to stop at some point. And when I is, if you pick I to be, say, 2 plus log base 2 of alpha divided by epsilon, something like this works. Because you can't get beyond there. And what that means is that something went wrong in the key lemma, and the only way that can happen is if you got down to a subspace which was smaller than 4 alpha over epsilon. So you'd have to have gotten down to, one of these HIs would have to have violated that. And on the other hand, the codimension goes up by at most 1 exponential at each step. And so you only have a logarithmic number of iterations, and so you end up getting a tower height, which is essentially logarithmic number of iterations, which is essentially log of alpha over epsilon as an upper bound, once you have this key lemma. Okay, so I want to say a few words about the proof of this key lemma, how you can get this density increment. Is there any quick questions before we move on? Okay. So, well, the proof uses arithmetic analogs of the Friese-Cannon weak regularity lemma and an associated counting lemma. So what do these weak regularity lemma and counting lemma look like? So in general, instead of looking at a subset, it's more convenient to look at a function from fp to the n to 0, 1. So you can think of this as a characteristic function of your set A. And if for H a subspace of fp to the n, we call H delta weakly regular if for all characters chi f minus fh, the Fourier coefficient of this function, of x is less than or equal to delta for all x in fp to the n. Oh, chi, sorry. For all chi. So I haven't said what fh is. It's the averaged out function. So it's constant on each of the affine translates of h, and its value is the average on those translates. So the weak regularity lemma says that for all f from fp to the n to 0, 1, there is a subspace H, which is delta weakly regular and is small. And the codimension of H is at most delta to the minus 2. And in fact, when we apply it, we really want it just to be equal to the floor of delta to the minus 2. We don't want it to be too small. So there's going to be a delta weakly regular subspace of small codimension.
How does this compare to Ben's regularity lemma? Like, what's the?
So this is a weak regularity lemma. It tells you globally what's happening in large subspaces, but doesn't tell you about what's happening in the affine translates of H. So so Ben's original arithmetic regularity lemma, and in the work of Ben and Terry, they have essentially this as well. In the strong version of the strong regularity lemma that we mentioned earlier, you get control on the densities inside translates of H, inside these codimension 1 subspaces of the translates of H. And here it's more about global density. So in large affine subspaces, you get the right, of the whole fp to the n, you get the right density. That's essentially what's going on here.
And the codimension here is much smaller than.
The codimension here is much smaller, yeah. So instead of tower, it's only polynomial, the codimension. Yeah. And there's associated, so the proof of this is basically you look at f, you look at the large Fourier coefficients of f, and you pick h to be the subspace of all vectors which are orthogonal to all of these large Fourier coefficients. And then this follows pretty easily. And the fact that it's at most delta to the minus 2, so large here means that the Fourier coefficient is at least delta, and this follows from Parseval's identity.
So you do it in one step.
Yeah, there's no
No
iteration.
iteration.
No iteration, yeah. So the way we originally wrote it was through iteration, and Ben showed us that it was much shorter this way. Yeah. You do an iteration, yeah. But you probably can use eigenvalues and do it in one. Probably, but I haven't checked it. Yeah, Terry found a spectral proof of the graph regularity lemma, and it turns out that you can get the arithmetic regularity lemma if you follow the spectral proof of the graph regularity lemma.
Yeah, there are some older spectra.
Right. Right, yeah. So actually, Friesen can, yeah, have as well, yeah. That's true. Okay, so in addition to the weak regularity lemma, you have a counting lemma. Which goes well with the weak regularity lemma. So again, you have this f, which is a function from fp to the n to 0, 1. And you have this delta weakly regular if h is delta weakly regular. Then the count of 3-term progressions in f minus the count of 3-term progressions in this averaged out version. So they're close to each other. So it's at most 3 times delta times alpha, where alpha is the average value of f. Now, this thing here I said is the 3-term arithmetic progression density. It's equal to the expected value over x and d in fp to the n of f of x, g of x plus d, h of x plus 2d in general. And you can write this difference as a telescoping sum of 3 terms, and each of them have an f minus fh in them, and each of them are bounded. And then you can apply Cauchy-Schwarz and Parseval's identity and use this property. So you use that. We have a formula for this in terms of Fourier coefficients to start with, and then you can quickly get the counting lemma from that. Okay, so I've run out of time. I wanted to go through the proof. I'll tell you the big picture idea in 1 minute. So now that we have this subspace H, we in each of the affine translates of H, we're going to apply the weak regularity lemma. So in each affine translate, we're going to separately apply the weak regularity lemma. We'll get some weakly regular affine. We'll get some weakly regular subspace of each of these affine translates. And then you can approximate the 3-term arithmetic progression density using the averaged out version in each of these affine translates. So we're going to count the total number of 3-term arithmetic progressions with common difference in H. And we know that that's going to be small because for every D in H, we know it's going to be small. Except the 0 one, we don't know there, but that's going to be negligible because H will be big enough. Okay, and then inside each of those, we get some formula. We can apply one of these inequalities from Olympiad mathematics, Schur's inequality, and to these densities, and you eventually can rearrange and get this sort of inequality from that using the averaged out versions. And the averaged out versions, we know that they're close to the density of 3-term progressions in H using the counting lemma. And then what we're looking at, the H prime is going to be the common refinement of H and all of these subspaces we found for each affine translate of H. And so the codimension will be the codimension, at most the codimension of H, plus for each affine translate, we're going to get some codimension, and because there's p to the codimension of H affine translates, we're going to get a lot of, the codimension will go up a lot because of that. So because I ran out of time, I didn't go over the details of that proof, but it's not so bad. And there were a lot of other things related to this, but since we're out of time, thank you very much.
Are there any questions?
So you mentioned in response to Ryan's question that you could find lots of Ds.
Right.
For your theorem to hold. Do you have any idea what such a set of Ds might look like?
Yeah, so what you get in the end is you get a subspace H so that the average density of 3-term arithmetic progressions with common difference in H is going to be at least alpha cubed minus epsilon. So you're going to find a subspace where the average value is at least alpha cubed minus epsilon. And then if you want to give up another epsilon there, you get a huge fraction of those elements. So there's going to be a big subspace where a substantial fraction of those D inside that subspace will work. I didn't say about the general case, if you're looking at the integers or general abelian groups, there you have to use Bohr sets and try to get all of these ideas to work in the Bohr set case. And there's substantial difficulties there. And in that case, you get some big subset of a Bohr set that will be your Ds that work for you.
In the lower, so you didn't say about the lower bound at all?
Yes, so I should then give a preview of the next talk. Yufei Zhao will give the lower bound.
In there, what would be the set of these?
So there you want to say if n's not too large, then you're going to be able to make a construction where there's no d that has
Right, yeah.
that has yeah. And yeah.
In there, it would behave more or less the same for different things.
For different
For different values of these, it would behave
For
more
all
or less the
these,
same. It would
the alpha
have
cube.
the same density roughly for all these.
Not really.
You'll see.
Yeah, not really. Yeah. As you can see here, this mean cube density it goes up at each step because of convexity, and so as you get these smaller subspaces, the average value inside those goes up, and you have to battle with that at each step, and that's where this logarithmic tower height is coming from. So basically, the whole idea is to reverse engineer what's going on in the upper bound and try to make a matching lower bound construction. While this works, this is the right sort of lemma when epsilon is small. When epsilon is big, you actually get a much bigger increment. This b of h prime divided by alpha cubed goes up in the exponent of each step. Instead of you get a multiplicative factor, you get a 1 plus 1 over 2 CP, where the CP was from the arithmetic triangle removal lemma, was that exponent. And so that's where the log is coming from. You're going up in the exponent of each step. And there it's a very different proof. You have to apply the supersaturation version of the Capset result after applying the weak regularity lemma and counting lemma at each step to get a bigger density increment. So a lot of the subspaces basically become empty. And then a few subspaces get much more density, and it gives you a much bigger density increment. Yes?
So, it's like a general question. Is there any removal type lemma that we know weak regularity won't suffice and we need strong regularity? Or at this point?
Well, for the removal lemma, the way that the improved upper bound comes is from repeatedly applying the weak regularity lemma, which is basically the same thing as what you're doing in the regularity proof. The logarithmic tower height, instead of the polynomial tower height, is that you can do this where you get a better density increment at each step, and so you don't need as many iterations. So in some sense, we're doing something like what's like full regularity still in the triangle removal lemma proof. And these new proofs that work in the arithmetic setting are based on both using the algebraic polynomial method and combining it with random sampling and combinatorial ideas. And they're very different than the sort of regularity and Fourier analysis type approaches, these much more analytic techniques. Yes?
Is there any graph theoretic analog of this sort of popular
differences? Yeah, I was looking for some. I don't know of any yet. It's a great question. There's a lot more freedom in graphs. So subspaces here are playing the same role as subsets of vertices in graphs, and those are much more general. Subspaces are much better behaved, and so I don't know of any good examples yet in the graph world. One question that Ron Graham asked me was, can you get other things like this where you get even bigger bounds than tower of height logarithmic? And if you replace alpha cubed by the mean cube density, then Ben's upper bound proof gives a tower of height polynomial 1 over epsilon, and you can go through the lower bound construction that Yufei is about to show us, and get a tower of height, a power of 1 over epsilon. For that, it's a little bit bigger tower. And then he was asking, what about Wowzer, which is next up in the Ackermann hierarchy? And you can reverse engineer the strong regularity lemma to get some applications that look less natural, but you do get Wowzer type bounds for those applications that have to do with three-term arithmetic regression density and things of this flavor. There's lots of other variants that one can look at. Ruja showed that for 5-term progressions, instead of 3-term, the natural analog would be alpha to the 5 minus epsilon. That it's not true, that there is no theorem like this. But Ben Green and Terry Tao developed a more general arithmetic regularity lemma, and they used it to apply for the 4-term case. So we know it's true for 3 and 4, and it's false for higher values, and there's some very interesting things going on there. There's many other variants and things going on, and we're looking at a bunch of them now. Yeah.
Well, we've timetabled some very generous coffee breaks in this workshop, so maybe if there's more questions, we could ask them over coffee.
Okay.
Thank Jacob again.
Thank you.